weekend and just hasn't gone away. So it sounds a little weird, but hopefully the talk won't be so crazy. I want to talk to you about neutrino physics. This is a program that we intend to pursue at the Oak Ridge National Laboratory, where they're building an accelerator there. The accelerator is used to produce neutrons, however, not neutrinos. Still, the power in the beam is sufficient that, and I'll talk about this a little bit later on, to produce a large flux of neutrinos in addition to the neutrons. And we intend to use the neutrinos here for some experiments, in particular experiments that have some astrophysical interest. So I want to talk to you about neutrinos at the spallation source, SNS, if you will, so, at the Oak Ridge National Laboratory, with respect to neutrinos. So let's see, these are some of the collaborating institutions. I put some stars up there about the people that are involved in this particular project. Give appropriate credit. Let me talk a little bit about neutrinos. I am sure most of you know something about them. I'm not sure exactly where you are with the understanding of neutrinos, so I'd like to give you a little bit of some background, some elementary background about neutrinos. Back in 1930, in looking at the decay, beta decay of, got a pointer someplace.
There's a laser on there.
Beta decay of either neutrons or protons, depending upon the actual particle. And this just shows a neutron here, but this neutron could be embedded in the nucleus. In any event, when one measured the electron spectrum from this decay, you found that it did not come out in a monoenergetic line as it would if there were only two particles in the decay process. This was a continuum spectrum with an endpoint, and Pauly said that, well, there must be something which is being observed which carries off additional energy and momentum so that you can then conserve energy and momentum in this particular process. The comment was, when he proposed this, that he's a little embarrassed because he didn't think this particular particle would ever have been seen. It turns out now that we see them, and in fact that we do a lot of things with neutrinos. You know, I think that neutrinos have very small mass. We don't exactly know what they are, but what the mass is, but it's certainly smaller than an electron volt. Left-handed ones are the only ones that interact, and they interact very weakly. That is, they interact via the weak interaction. And we know that there are 3 generations of neutrinos, and perhaps more, but at least we know that there are 3 generations at least, and that lepton number is conserved. So that means that if a neutrino has a electronness or a muonness or a tauness, presumably it gets conserved, except for the fact that they have masses now, and then these particles actually get mixed together. My understanding is that the present particle data book is going to start listing neutrinos as neutrino 1, 2, and 3, rather than to talk about them in terms of their flavor. So what about the neutrinos? Well, we don't know whether neutrinos are Dirac particles or whether they're Majorana particles. If they're Majorana, that means that they're their own antiparticle. If they're Dirac, of course, that means that they're 2 separate neutrinos that are involved between the neutrino and the antineutrino. We don't know the masses of the neutrinos, which is one of the full things that one is trying to measure these days. We don't know the mass hierarchy. We don't know whether the lightest neutrinos are the electron neutrinos or whether they're inverted. CP, charge conjugation parity, time reversal. We don't know whether that's violated in the neutrino sector. And in addition, we don't know whether we know about all the neutrinos. I told you that there were 3 types, but originally there was a possibility of having something called a sterile neutrino, which means that if it ever went into a sterile neutrino, you'd never see it because it doesn't interact with anything. That's why it's called sterile. There was some evidence that perhaps this was the case, but nowadays it's not believed. But perhaps there are some very heavy neutrinos which would explain why this mass is so small. What are the mixing angles? If they have masses, all of these neutrinos mix together, and that can be written down in terms of a parameter called the mixing angle, which tells you the strength of this mixing. Some of that mixing has been measured, but this particular one, which measures a tau into an electron, for example, has not been measured, and it's one of the fundamental, not showing up so well, but the one down here on the bottom is how do neutrinos affect the evolution of the universe? And that's what I want to talk about. Neutrinos do affect the evolution of the universe. It is important that we try to understand this. I want to spend a few minutes talking about that. So, how do neutrinos affect the evolution of the universe? Mr. Newton said that if you look at his laws, there's a certain thing called fixed stars or whatever that you can refer all reference frames to. We know, of course, that's not true anymore because we have general relativity. But that at least comes with the idea that the universe is somehow fixed. There's not anything that's changing in the universe. But that's not true. The universe is evolving from the Big Bang to today even. There are things that are going on in the universe from making new elements to stars to whatever. And so the universe is constantly changing. How is it changing? Well, neutrinos have a large role to play in this particular change. Neutrinos and the weak interaction in particular, electron capture, for example, are believed to be crucial in core collapse of type 2 supernova. And we want to know why this happens. This is the famous nova here, 1987A. This was the picture that was made right after it was discovered. This was a picture made 10 years later of this particular supernova in the X-ray region. Explosion here, still 10 years after the event. Supernovae apparently are the dominant contributor to galactic nucleosynthesis. We want to understand why that's the case. They seem to occur in a collapse of stars that have iron core and something on the order of 8 to 10 times our sun's mass. And they are extremely energetic. In fact, neutrinos carry almost 99% of the energy out of a supernova. So the universe is actually flooded with neutrinos. There are a few per century in our galaxy. In fact, some people say there's as many as 15 a year, but we just don't see them. But in any event, presumably there's a few per century, and the last one that was actually seen in our galaxy was about 400 years ago. So we're due for another one here sometime soon. Here's sort of what a supernova looks like. It actually is a star which is toward the end of its life. It now sort of forms different shells. There's something called a proto-neutron star on the inside, which was basically an iron core which is being squeezed and now turns mainly into neutrons. Out of this particular core, neutrinos flood into this particular region out here, which is mainly a gas of neutrons, protons, and probably alpha particles. At this point, the neutrinos can interact with particles or either electron capture here, but they move very rapidly through this particular area, while in this area down here, they more or less diffuse. They hit this area on the outside, which is basically a nickel-iron shell. Because of the interaction, which I'll talk about here a little bit later on, they now can deposit their energy in this particular shell, and this presumably causes things to actually explode. So what happens is the star starts to collapse, it bounces, there's a shock, which then stalls here at that point, and then this additional neutrino flux which comes out from the heating of the inside core then causes this shock to reoccur and causes the explosion. At least that's the current thinking about what happens. The problem is that when people run these particular programs, they calculate what goes on. Sometimes they get an explosion, sometimes they don't get an explosion. So we're not quite sure what's going on. One thing that one looks at here is, here's the proton-neutron star, here is the emission and neutrinos which come off, and in this region here, you have to really do the thermodynamics correctly. There's all kinds of diffusion, there's all kinds of turbulence that occurs, and up here, there's this stall shock, which then gets blown off by this hot gas mixture on the inside, which is mainly being driven by the neutrinos. In this region here is where quite a bit of nucleus, and of course, when the explosion occurs, all of this is thrown into space and acts then as the birth of, here's a supernova explosion simulation anyway. You saw the bounce come in here. The time over here is actually in seconds, okay? So this is like a quarter of a second, and all this is actually going on. Turbulence occurring, and then all of a sudden the explosion happens. All the bounce, it starts to come back in. All the infall keeps coming in, all being heated by the neutrinos, which, so I just need to go one slide down. There you go. Okay, so here's the neutrino production that comes out. Okay, type of neutrinos. Now you can see the time up here with their occurring. I mean, this actually is something again like a quarter of a second, and all these neutrinos at that point. I ask you to do it again. If I got a movie here, apparently it's going to get hung up on this. So neutrinos interact. Neutrinos are one of the prime drivers for nuclear synthesis, and this just says a little bit about how this occurs. I think I've already been over all of that, but the point being that cross sections are extremely important to understand how supernova explosions occur. That I'll address here in just a minute. So electron capture again. Every time an electron gets captured of a nucleus, and then you have the inverse process that goes on. So it comes off a neutrino and then captured. All these things go together. So to calculate all these rates, which have to go into these very large computer programs with hydrodynamics and other things that are involved in it, all of these things have to go in here correctly. All right, so the weak interaction is crucial in understanding though is transporting energy from the core here. Gravitational energy, as the core collapses, changes towards that gravitational energy, the exterior, and then interact with the shells on the element. So supernova explode. They also produce new elements here, and this shows how you calculate these things. Go at least up to A equals 60 or 65 using the shell model, but when you get up into regions up here where you really want to know how this portion of the periodic table is actually populated, density functional theory or shell model Monte Carlo, but you really can't do a good job in this region. Why experimental measurements are needed. All the masses of these particular objects, not the masses of the neutrino, masses of these different elements. You need all the weak decay properties, the electron capture, neutrino interactions, and all the thermal properties that are involved in order to be able to do it. It is a convolution of new structure, astrophysics actions. This is another movie. Simulation. Assume that I have a silicon shell. There's the silicon. Now I'll let neutrinos and other particles interact at this particular on this shell, and goes the shock through that. And you can see the population here of all of the elements as they're being. So it takes something, populates all of this. Okay, there are two types of cross sections that are important here. Charge current cross section, where a neutrino comes in and makes an electron here, where lepton flavor being conserved because you come in with a neutrino, electron type neutrino, and you make a electron on the outside. If you came in with a muon, it would want to make a muon neutrino, it would want to make a muon over here, but it's got to have enough energy to make the muon, which is 105 MeV. So you would not be able to make that particular process unless this neutrino had sufficient energy. Changes a W plus boson, in this case it was interacting with a neutron making a proton, but it also could exchange a W minus and go proton to neutron. In any event, The charge current interaction is something that one wants to measure because the inverse of this looks like electron capture. So you not only need the forward but the backward process involved. This is a description mathematically of how one might calculate that. These factors here contain the form factors, the vector and the axial vector form factors of the nucleus. So, knowing the nuclear physics, presumably calculate these cross-sections. The inverse is cross-sections. If you measure them, you can fill their parameters. The other cross-section is in neutral current. In a neutral current, the neutrino comes in and simply scatters off of a neutron or a proton or something like that, and it's not going to change. So in this particular case, electrons, neutrinos could scatter, or muon neutrinos, or tau neutrinos, or antineutrinos. They could all scatter and deposit energy. So neutral currents are going to be important for transporting energy from the inner core to the outer core, because you saw that when these neutrinos were being produced on the inside, they were producing both neutrinos and antineutrinos and also muon-type neutrinos as well. But the muon neutrinos, all these energies you'll find are too low to actually produce muons. So they will, in fact, scatter by neutral currents, transferring energy by that mechanism, but not only the charge current work in the case. This shows the coherent elastic scattering. I'll talk about coherent scattering here in just a minute for this particular process for the neutral current. And it's also sensitive to the magnetic moment if the neutrinos had a magnetic moment. And this shows the equation involved with that. T is the actual recoil energy that's involved. There's a singularity here of 1 over T. Actually, it's not singular when you sit down and work it out, because there's going to be a threshold for a low value of T. But in any event, the point is that you want this threshold as low as possible in order to be sensitive to measuring the magnetic moment. And the shape of the spectrum is a function of different for these two processes. So one might be able to tell. So we want to measure neutrino nuclear cross-sections. Both cross-sections are going to be needed. We need a whole bunch of changes and effects to be in here. The only cross-section that's actually been measured is a charge current cross-section, and it's reasonably well measured. That means it's measured at 10%, but there's no other cross-section actually that's measured. Coherent nuclear scattering has never been observed. It's certainly there, but it's never been seen, and the reason it hadn't been seen is because of the threshold problem. Again, something I'll talk about in just a minute. And all of these things are needed if, in fact, we're going to build neutrino detectors to look for astrophysical neutrinos. One of the things that was left over from the Big Bang is neutrinos. And so we know that we're looking at the cosmic microwave radiation, but it would certainly be nice to look for neutrinos, which came from that particular explosion as well. And so you'd like to be able to large detector and know that you were sensitive of that energy range. One of the basic interaction, which gives you the actions that I just talked about, scattering off of a nucleus, is something like a carbon nucleus down here. And you can see between the spin here, the isospin being 0, and it goes up to the isobaric analog state here on either side, and try to do nuclear physics carbon, the same thing I had before. This is a calculation for iron, charge current cross-section, and shows the charge current cross-section here as a function of neutrino energy. Large here, Gamow-Teller transition, and the second largest one, which in this range. Calculation, not a measurement. It shows, in fact, that neutrino comes in and scatters here in a charge current reaction. The electron comes off at an angle theta. This is back angles. As the energy goes down, and these are energies now starting to get into the range from 50 MeV down to 0, starting to get into the range of supernova neutrinos, it shows that the cross-section actually is backward peaked, not forward peaked here. So one would like to be able to measure this angular distance. Because the neutrinos that we're dealing with are so low in energy, somewhere, let's say, around 35 MeV or so, their wavelength is actually rather long compared to the size of a nucleus. Here I'm looking at various types of nuclei, but this particular noble gas here of xenon would have a radius of about 13 Fermis or so, and this wavelength is much larger than that. So that means that this neutrino can interact with all of the nuclei here and hear it. So basically what you get is a cross-section which is the square of the number. That's why this particular cross-section is so large, and that's why the neutrino interacts so readily with an iron core, because it is actually able to get out, pass through the neutrons that surround this iron core very easily, because they only have an A of 1 or 2, or if it's an alpha particle 4. But when it hits the iron, it hits this 56 squared, and that cross-section is so large that it deposits essentially all its energy in that shell core. In any event, the point is that this recoil here is very low, and so one needs a detector which is sensitive to very low recoil energies. Here again is the accelerator, a linear accelerator with a ring. It's a 1 GeV proton driver. It runs in here, hits a mercury target, makes a lot of neutrons, and our experiment would be somewhere in this particular range over here. It's called CLEAR. Shows the machine parameters, primary beam energy, and whatever. I have another one in here which is a little bit better than this, but the point is that this makes a lot of neutrinos here per year. So what kind of neutrinos does it make? Well, this makes neutrinos by the stopped process, where the proton comes in, hits the target, there's lots of fragments which come off. In fact, that's what you want, because this really is supposed to make neutrons for solid state research, so that all these neutrons. But in addition to that, it's going to make pions. The pi minus get atomic captured, and so they disappear. The pi plus, because they will not atomic capture, come to rest. They decay into a mu plus and a muon neutrino. Then the mu plus is stopped also in the target, and then it decays into 2 neutrinos with an electron. So this is a stop target, and it provides you with a very nice spectrum of energies of neutrinos, those in the range that one would like for supernovas. There were a couple of other stopped beams. One at Los Alamos, it's still running at LSND actually. The other one in at Carmen, and that one is no longer. This is a spectrum of neutrinos which come out from the stop pion facility. You can see it goes up to a maximum here of something like half the muon mass. Is a anti-muon neutrino. The muon neutrino which comes out here, remember, comes from a 2-body decay process, so it's monoenergetic, and then you have the electron neutrinos in here as well. And in addition, the beam is pulsed, so that you get a pulse of neutrinos which come out at different times. This one is very long because this one comes from the decay of the muon, which has a decay time of 2.2 microseconds. So while the beam is much shorter than that, you can actually use timing to sort out not only the type of neutrinos you're looking at, but also to get rid of backgrounds. This just shows the decay process for the neutrino arrive. What I've done is to take that spectrum here that we just looked at, which is from the stop pion, and put this on top of a spectrum of neutrinos that come from supernova. The energy scales are the same, so this goes up to like 60 or so at this point in time. That's 6 scale over here. You can see that they reasonably match in terms of the types of neutrinos. So this is an important energy window that these stop pion facilities have. They're just right for doing the type of research for. A lot of neutrinos which are being made. Here are the different facilities and whatever. This is the SNS. This was made just to show the advantages of using SNS. We will have essentially more energy, more current, more hours run, and because of the timing, we have better control over what goes on. Look at a whole bunch of targets, value, types of detectors. One is a charged current detector, and the other is to look for the coherent neutrino nucleus interaction. Charged currents are going to look for the electrons which come out from a process like this. the coherent is going to try to measure the recoil nucleus. So let's look at the easy thing here first. This is the charge current reactions. The charge current is going to have two types of detectors, one called the homogeneous, which is just a liquid-filled tank, which could be a scintillator, but it also could look for Cherenkov radiation for the electrons in the tank, and it's filled with phototubes. There's also a segmented or a detector which is measuring ionization. Fairly large, but not that large, only at either and solid. But you want a solid material target because you want to measure things like iron or lead or whatever, and you can't really find some way to dissolve that material into the liquid, at least, and keep a clear liquid. So we need a solid target to do that. Here's a way of building a detector called a segmented detector element. This has a set of corrugated foils which surround some tubes here which measure how the electron which comes in this way actually goes. This is sort of a cross-section as you look down on top of it. Here are the foils around the outside. So the neutrino interacts in the foil. The electrons come off and penetrate through this, and you actually do tracking. What we need to know is how far the electron goes and whatever. Here's a track of neutrino interacting with iron, giving you the electron, and going to a cobalt. This is an excited state now. I think this was calculated with isobar analyzed state, but whatever. Here's a track, and it started off here, and look, it does not go in a straight line, and that's because of the multiple scattering of the electrons. Sooner or later, the electron slows down sufficiently so that it interacts with the foil and now goes through large angle multiple scatters. So the issue is, can you figure out, did the electron go this way or did the electron go that way? Because you want to try to do a angular distribution. It's not so clear. This one probably is a clear one because this one had a big kink at the end of it, but some tracks don't. And so you really need a way of determining which way this particular electron actually would act like that. So we come up with a revised detector geometry. This one has several wires. This just looks like a potential map of what that detector looks like involved. But here's the way you do it. The initial particle comes in, and you have a straw detector here, which has an ambiguity. It either went this way or this way. But by connecting this through the detector here, and by doing a Monte Carlo least squares analysis, sort out how this thing actually measurement of the probability that here's some cross sections that one would try to measure. You see they're down into the 10 to the minus 43 centimeters squared, but the SNS delivers sufficient number of neutrinos and the target's big enough, so several hundred events. So that's the charge current detector. If you want to try to measure coherent scattering, what you need to do is you need to have an extremely low threshold. And very recently, there's been a lot of development of detectors using liquid noble gases. This is just properties of various liquid noble gases. Xenon and argon probably are the two that are the most interesting here. There are two things that are involved here. One is the electron mobility. And of course the other is the actual size of the nucleus here. And that determines not only the cross-section, but also the energy, the relevant energy as well is actually going to have. Here's a two-phase liquid xenon detector. These detectors are used for weakly interacting massive particles, WIMP searches, or a lot of other very low threshold searches. And takes advantage of the very high mobility of electrons to produce two types of signals. The event occurs here, and so you get some scintillation light from the event that occurs, and then the electrons drift to the top up here where they're accelerated and also produce ionization in the gas, the second phase here just above the liquid xenon. So you get two signals. You get an S1 and you get an S2. An S1 being the nuclear recoil interaction and an S2 being the ionization signal that occurs up here. Signals are different because the nuclear recoil here inched talk for just a minute about what quenching means. Here's what the signal actually looks like when it comes out. Here's time of the signal that you see, the light which comes out of that particular scintillation. This is normalized up here. This signal right here is what happens for gamma rays or for electrons. That energy is going to be spread over a larger range than the nuclear recoils, which is over a smaller range. And so this is going to be suppressed with respect to this because there's quenching involved. These states get quenched and they don't produce light. So if you make a measure of this amount of light, particularly out here, you can tell or discriminate between whether or not you had a nuclear recoil as opposed to an electromagnetic interaction. Factor here for quench factor here for the tangent. The result is this particular slide here came from the WIMP search, which was published in FISREV letters, and this was actually used to try to search for WIMPs. They plot one signal versus the other signal, and you can actually a calibration where the nuclear recoil from beryllium, which produces neutrons, produces nuclear recoils, and this one, cesium-137, is a gamma ray. You can see that this line here, which would be the electromagnetic, and you see here, is all around that line. This line here, which involves nuclear recoils, is down around this lower line that we have right here. So there is a discrimination, and you need a discrimination in order to be able to get down to very low thresholds. We want to get down below 5 kilovolts here in order to be able to be what the detector would look like, sort of hydrogen cooling. Part of the detector with top and bottom placed at this point. The whole thing is sitting inside of a big water tank right here. Person to give you the size of the actual tank itself. The water tank is used for, remember that this particular accelerator is making neutrons. That's what it wants to do. That's why it's there. And so we've got a lot of neutrons floating around. We can't stand to have neutrons in our detector, even though we have some discrimination against them. We've got a water tank and that for shielding. Shows the threshold here, function of the counts per year per ton that you could have, and we want to be some 5 kilovolts. That if I were to look at what this energy is here, threshold down here, capture is part of the recoil. A simulation of the signal background that once take this area right here, and background which comes from this is a calculation of the actual flux of neutrons and gamma rays, color-coded here. Here is a steel wall. Here's the water tank. Here's the detector on the inside. Here comes the neutron beam. This, so you can see it's hot in this area and then cools off as it gets on the side in here. So we want to try to work out what by changing things around, what the shielding is. It looks as if, see, this was done for the calculation for this right in the middle of the tank. Obviously it wasn't the right thing to do. It would be sitting over here top. It should be sitting at the bottom of the tank. So a lot of things that one can do. We can also place time. We also have cosmic rays which come in. Cosmic rays are not a problem in this case. So here's the estimated yield per year for the charge current reaction for targets that we have here. You can see 5 and 10% all the way from iron. For the neutral current, we would expect to get something on the order of 200 events. Remember, this cross-section has never been seen. We might be able to make a measurement of the Neutrino magnetic moment to something on the order of 10 to the minus 10 megatons. That's about where the present limit is, so this is not such a can extract information on the standard model, the weak charge, for example, measured here. But we're not really sensitive enough to that to be competitive with present measurements. Could, however, improve non-standard interactions to the standard model on the order of about a factor of 10 or so, something like that. And as I say, we can measure, it's measured in a different channel, maybe food, by saying that neutrino interactions are very important for supernova. We need to make these particular measurements in order to put them into calculations, simulation codes in order to be able to determine whether or not we really understand what's going on. The SNS provides us with a unique opportunity to make measurements here to extremely accuracy in a year. We have to do this, and we would like to make the first measurement this ever of neutrino astrophysics. I think is awesome. Website.
All right. Questions?
Isn't there a tremendous difference between neutron production and neutrino production? Do they interfere with each other to any extent?
No. There would be no interference because these are separate particles, so I'm not exactly sure what kind of interference you're talking about.
Or background?
Well, background is a problem, obviously, because the beam comes in, hits a mercury target, and spalls the mercury target, so you're knocking neutrons out of that target. In the same process, you're making pions and muons, and it's the decay of the pions and muons that you're actually looking for the neutrinos. There are lots of neutrinos which come from the beta decay of the radioactivity in the target itself, but those are much too low energy for us to we would be better off looking at a reactor neutrino than trying to use that.
There's apparently more neutrinos than the other particles.
Yes.
Why is it less importance put on the research?
I don't know that it's less important. It requires substantial amount of investment in dollars and time. The detectors are really large. They're very expensive, and it takes a good time to make these kinds of measurements. So someone who wants to go into this particular business would want to spend 10 or 15 years of your life making measurements like this, and you would need dollars to do it. Now, this particular proposal here that we have proposed is on the order of $10 million, so it's really cheap, small experiment that will be useful within a year or two. So that has, to me, more attractiveness, I think, I would say, than other types of neutrinos. But look, I mean, people are making neutrino measurements now. Well, they've already seen geophysical neutrinos. One of the things that you'd like to do is to measure what goes on inside the Earth. So you'd like to measure the neutrinos would come out of the radioactivity inside the Earth. People have done that now, measurements made of that, but you might want to make this measurement at different places on the Earth's surface to see what we're. So there's geophysical interest. As I mentioned before, there is interest in measuring relic neutrinos from astrophysics. So I think things are just getting started, and from my perspective, for the next 10 or 15 years, neutrino physics is the hottest topics around. Yeah, well, that's a problem, of course. We have to get money from the Department of Energy or somebody to do this. We've had a proposal into the Department of Energy for a year. The Department of Energy thinks it's a good idea, but they don't have any money. We've just submitted another proposal for the coherent scattering to the National Science Foundation. The results of that, if we are funded, within 2 years we could do the waiting for money. SNS is on schedule to start. Well, they're already producing beam. They've already been measuring backgrounds, neutrino backgrounds there. So the SNS will come on in a year or so, more or less at the power, which is 1.4 megawatts. And they probably will attempt that by maybe a factor of 2. Which means
last bullet, the second to last bullet talks about collaborators, additional collaborators.
Mm-hmm.
Are members like you with that?
I have 2 students that are working for me at the present time that are both doing some initial calculations. If we get funded in the near term, that will work. If the funding doesn't come through, then they'll obviously have to go do something else in order to be able to fill. Right now, one of the students is doing simulations of neutron backgrounds using models that simulate neutrons, interactions, and whatever. The other student is making a calculation of the neutrino flux with top target. We need to know that very precisely, so that means you have to write a Monte Carlo code, or you already exist.
which looks at the production of pi's and mu's and mercury and stops them, and then determines how many neutrinos come out and whatever. So all that has to be done. Those two students are doing that now. That's not sufficient for a doctoral degree, but
This machine you're talking about in particular, not being optimized for.
it's optimized for neutrons. It's optimized for neutrons.
Neutron, yes. So
Yeah.
does it make any difference in terms of total output of the experiment?
Yeah, sure. If they were to optimize this machine to make neutrinos, you want to make as many pions as you can, and we would attempt to change the structure of the beam and to do other things. But they're being funded to make neutrons for neutron research, and what we're doing is we're getting the beam for free. So. Well, I worry about things like that, but so far our simulations indicate that we're doing a good job with that. Remember that they've got to do something. They can't just have all those neutrons floating around anyway, because they're going to be people in the area, so they have to do shielding themselves. So we're shielding on top of shielding, basically. I ran over it really quickly, but I showed you the flux of neutrons. I have a slide here which shows you the flux of neutrons. Most of those neutrons actually come from the instruments themselves and not from the target. Most of them are coming out the back end of their scattering instruments. Yeah, I don't know if I can go back here and look at that or not, but
Go to slide,
probably
maybe?
not. Huh?
Yeah.
It's way far back. If you can back to the neutron. Are you going back up? I want you to go forward from where you were. No, the problem is that the neutrons are made all the way up to the maximum beam energy. Well, not many of them made up there, but they're made all the way up there. The neutrons that we actually see are not primaries. They are coming from other things. The energetic neutrons make other neutrons, and so it's this process of all this background comes in. So it's shielding. That's the RTBT and neutron instruments. The RTBT is the transport line for the beam. So that's the beam transport line. Neutrons from instruments. This is what's coming from the target here. This spectrum. Well, these out here, which come in, fall from shielding and other neutrons, and that's the real problem. But use the spectrum into the simulation, and what happens? Simulations are pretty good. I won't claim that there's 10% accuracy on this, but it's good.
Okay.
Okay.
Any other questions? Let's thank our speaker.